Reducing power plants' thirst. Body made Latin right, and collaborators developed a more efficient cooling system for power plants. Together with Pat Brady left, the Sandia National Laboratory research are also developing a first of its kind system dynamics analysis to identify water-saving technologies for cooling at power plants. Credit Randy Montoya. Body made the Latin right and collaborators developed a more efficient cooling system for power plants. Together with Pat Brady left, the Sandia National Laboratory's researchers are also developing a first-of-its-kind system dynamics analysis to identify water-saving technologies for cooling at power plants. Credit Randy Montoya. Electricity production is one of the industries that uses the most water in the country each day. Researchers at Sandia National Laboratories are helping the largest power plant in the United States identify the most efficient and cost-effective strategies to reduce water use. Electricity production is one of the industries that use the most water in the country each year. Researchers at the Sandia National Laboratories are helping the largest power plant in the United States identify the most efficient and cost-effective strategies to reduce water use. They developed a first-of-its-kind comprehensive system dynamics analysis that can show power plants with wet cooling system how it can save them money. The analysis could eventually be used at other plants as federal regulators begin to reduce the power industry's allowed water supply. The researchers have also redesigned and planted an air cooling system to make water-less cooling more energy efficient and possible over a wide range of operating conditions. They developed a first-of-its-kind comprehensive system dynamic analysis that can show power plants with wet cooling systems how it can save them money. The analysis could eventually be used at other plants as federal regulators begin to reduce the power industry allowed water supply. The researchers have also redesigned and patented an air cooling system to make water-less cooling more energy efficient and possible over a wide range of operating conditions. The Palo Verde nuclear generating station near Phoenix converts heat from nuclear reactions to electricity. The heat boils water, creating steam, and that drives turbine generators. Steam leaving a turbine must be cooled and condensed before it is reused. The Palo Verde nuclear generating station near Phoenix converts heat from nuclear reactions into electricity. The heat boils water, creating steam that drives turbine generators. Steam leaving a turbine must be cooled and condensed before it is reused. More than 40% of all the water used in the country is for wet cooling at power plants. Typically, large Thermoelectric power plants are located near lakes or rivers so that operators can draw a regulated amount of water, run it through a condenser to cool stream leaving the turbines and discharge roughly the same amount they withdraw. More than 40% of all the water used in the country is for wet cooling at power plants. Typically large thermoelectric power plants are located near lakes or rivers so that operators can draw a regulatory amount of water, run it through a condenser to cool stream leaving the turbines, and discharge roughly the same amount they withdraw. But the Palo Verde plant has limited access to water because it is in the middle of a desert. Its cooling water is treated wastewater, which is becoming increasingly expensive as other customers who are willing to pay higher price for water emerge. To curb rising costs, operators want to reduce the plant's water use by about 9 million gallons a day annually. That saving is roughly equivalent to a 16 square mile pool of water 1 foot deep, said Bobby Middleton, a nuclear engineer at Sadia. But the Palo Verde plant has limited access to water because it is in the middle of the desert. But the Palo Verde plant has limited access to water because it is in the middle of a desert. Its cooling water is treated wastewater, which is becoming increasingly expensive as other customers. Its cooling water is treated wastewater, which is becoming increasingly expensive as other customers who are willing to pay higher price for water emerge. To curb rising costs, operators want to reduce the plant's water use by about 9 million gallons a day annually. That saving is roughly equivalent to a 16 square mile pool of water 1 foot deep, said Bobby Middleton, a nuclear engineer at Sadia. Its cooling water is treated wastewater, which is becoming increasingly expensive as other customers who are willing to pay higher price for water emerge. To curb rising costs, operators want to reduce the plant's water use by about 9 million gallons a day annually. That saving is roughly equivalent to a 16 square mile pool of water 1 foot deep, said Bobby Middleton, a nuclear engineer at Sadia. Other thermoelectric power plants We'll be looking for water-saving approaches in the future as rising populations increase per capita energy usage and potential federal regulations reduce supplies of cooling water. The Sandia analysis could be used to save water at these power plants too, whether they run on coal, natural gas, or nuclear energy. Other thermoelectric power plants will be looking for water-saving approaches in the future as rising populations increase per capita energy usage and potential federal regulations reduce supplies of cooling water. The SADI analysis could be used to save water at these power plants too, whether they run on coal, natural gas, or nuclear energy. We jumped at the opportunity to tackle this problem for Palo Weather because solutions that work for Palo Weather could also work for other plants too, Mellon said. We jumped at the opportunity to tackle this problem for Palo Weather because solutions that work for Palo Weather would also work for other plants too, Mellon said. To reduce the plant's water use, operators at Palo Weather first looked at commercially available solutions. When they realized that nothing available could meet their needs, they turned to Sadia Labs to help identify which cooling systems under development might eventually offer the greatest water saving. To reduce the plant's water use, operators at Palo Verde first looked at commercially available solutions. When they realized that nothing available could meet their needs, they turned to Sadia Labs to help identify which cooling systems under development might eventually offer the greatest water saving. The wastewater that arrives at Palo Verde contains silica, calcium, magnesium, and phosphate ions. These salts concentrate as the cooling water evaporates in the cooling system, possibly forming new minerals that might clog the cooling towers. Currently, operators can lime, soda ash, and acid to the wastewater before it enters the cooling tower to reduce the possibility of mineral formation. The wastewater that arrives at the Palo Verde contains silica, calcium, magnesium, and phosphate ions. These salts concentrate as the cooling water evaporates in the cooling system, possibly forming new minerals that might clog the cooling towers. Currently, operators add lime, soda ash, and acid to the wastewater before it enters the cooling tower to reduce the possibility of mineral formation. Melton and Sandia chemist Patrick Brandy are using the model to identify less expensive ways to remove ions at different points in the cooling cycle. For example, the study researchers are examining the feasibility of desalinating discharged cooling water so that it can be reused. Otherwise, the water is too salty for reuse and must be evaporated from large ponds. Melton and Sadia chemist Patrick Brandy are using the model to identify less expensive ways to remove ions at different points in the cooling cycle. For example, the Sandy researchers are examining the feasibility of desalinating discharged cooling water so that it can be reused. Otherwise, the water is too salty for reuse and must be evaporated from large ponds. The researchers have finished the first phase of the project, developing the analysis software. The next phase involves using the software to identify the most promising water-saving technologies, including alternative water treatment approaches, as well as dry and hybrid coolers that use supercritical carbon dioxide instead of the standard refrigerants in using commercial technology. The final phase of the project involves testing the most promising technology in a laboratory setting in the hopes that a cost-effective solution can be installed at the power vendor in 2026. The researchers have finished the first phase of the project developing the analysis software. The next phase involves using the software to identify the most promising water-saving technologies, including alternative water treatment approaches as well as dry and hybrid coolers that use supercritical carbon dioxide instead of the standard refrigerants in use in commercial technology. The researchers have finished the first phase of the project, developing the analysis software. The next phase involves using the software to identify the most promising water-saving technology, including alternative water treatment approaches as well as dry and hybrid coolers that use supercritical carbon dioxide instead of the standard refrigerants in using commercial technology. The final phase of the project involves testing the most promising technology in a laboratory setting in the hopes that a cost-effective solution can be installed at the power vendor in 2026. Efficient cooling without water. While evaluating effective cooling technologies, study researchers also are working to improve existing solutions. Earlier this year, Melton and his colleagues were awarded a patent for redesigning an air cooler to use supercritical carbon dioxide to transfer heat from steam to air. This change makes indirect dry cooling feasible over a wide range of conditions while increasing the system's efficiency. While evaluating effective cooling technologies, study researchers also are working to improve existing solutions. Earlier this year, Dalton and his colleagues were awarded a patent for redesigning an air cooler to use supercritical carbon dioxide to transfer heat from steam to air. This change makes indirect dry cooling feasible over a wider range of conditions while increasing the system's efficiency. Wet cooling systems, such as those at the polar weather, have water-filled condensers to cool steam leaving the turbines. Direct dry cooling system transfer heat from the steam directly to air. Indirect dry cooling systems transfer heat from steam to water, then from the water to air. Current commercially available system designed to retrofit a power plant typical use recirculating refrigerants instead of water to help transfer heat to air. Wet cooling systems, such as those at polar weather, have water-filled condenser to cool steam leaving the turbines. Direct dry cooling systems transfer heat from the steam directly to air. Indirectly dry cooling systems transfer heat from steam to water, then from water to air. Current commercially available systems designed to retrofit a power plant typically use a recirculating refrigerant instead of water to help transfer heat to air. In this commercially available system, the liquid refrigerant boils as it absorbs heat from the steam and condenses into a liquid as it loses that heat to air. This change from liquid to gas release energy that causes the refrigerant to circulate naturally through a heat exchanger. In these commercially available systems, the liquid refrigerant boils as it absorbs heat from the steam and condenses into a liquid as it loses that heat to air. This change from liquid to gas release energy that causes the refrigerants to circulate naturally through a heat exchanger. The new direct cooler design uses critical carbon dioxide instead of refrigerant. Here's how it works. Above a certain pressure and temperature, carbon dioxide becomes a supercritical fluid. This means the carbon dioxide acts as a liquid below the critical temperature and as a gas above the critical temperature. However, at no point is the fluid a two-phase fluid. It does not boil, because one fluid can change from a liquid to a gas without boiling. A supercritical fluid can transfer heat over a wider temperature range than a subcritical fluid, such as the I-134A used in current technologies. The new indirect cooler design uses supercritical carbon dioxide instead of refrigerants. Here's how it works. Above a certain pressure and temperature, carbon dioxide becomes a supercritical fluid. This means that carbon dioxide acts as a liquid below the critical temperature and as a gas above the critical. This means the carbon dioxide acts as a liquid below the critical temperature and as a gas above a critical temperature. However, at no point is the fluid a two-phase fluid. It does not boil. However, at no point is the fluid a two-phase fluid. It does not boil, because one fluid can change from a liquid to a gas without boiling. A supercritical fluid can transfer heat over a wider temperature range than a subcritical fluid, such as R134 used in current technology. The performance benefits with this design come from the amount of air needed to refresh the superficial carbon dioxide for another round of cooling. A heat exchanger with supercritical carbon dioxide uses less air to cool water to the same temperature as a traditional dry cooler with a subcritical refrigerants. It can also make water cooler using the same amount of air. Both impacts improve the overall energy efficiency for the cooling process. The performance benefits with this design come from the amount of air needed to refresh the supercritical carbon dioxide for another round of cooling. A heat exchanger with supercritical carbon dioxide uses less air to cool water to the same temperature as a traditional dry cooler with a subcritical refrigerant. It can also make water cooler using the same amount of air, but both impacts improve the overall energy efficiency for the cooling process. The expanded operating conditions also means that there are more times of the year plants can use dry cooling, Mattern said. The researchers plan to test Sadia design against state-of-the-art commercially available technology, and they are currently analyzing it as a potential solution for a polyvolt plant. Due to the decreasing availability of water, what was once the cheapest resource for thermoelectric power plants is quickly becoming one of the most expensive aspects of electricity production. Water-saving technologies for energy production are critical for scientists and energy to consider today, Brandy said. Sadia National Laboratories is a multi-million laboratory operated by National Technology and Engineering Solutions of Saudi Arabia, a wholly owned subsidiary of Honeywell International for the U.S. Department of Energy's National Nuclear Security Administration. Sadia Labs has major research and development responsibilities in nuclear deterrency, global security, defense, energy technology, and economic competitiveness, with main facilities in Albuquerque, New Mexico, and Livermore, California. To evaluate different emerging technology, Meta developed software that combines the physics of the cooling process, such as fluid flow, heat transfer, atmospheric evaporation, and water treatment, with the financial impact of different solutions. Sometimes a certain technology saves a plant money through increased efficiency. Other times, reductions in water use deliver overall cost saving. No one has created a system dynamic analysis that simultaneously considers all these factors before he said it helps us predict the benefits we might see from a particular technology so that we spend time only testing the most promising technologies.